The last part of the last chapter is dedicated to high-frequency methods. High-frequency methods are applied to objects that are large compared to the wavelength. We could also, you already know how to solve problems using numerical methods. We are considering objects that don't have a canonical geometry, so analytical solutions are not possible here. And you already know from chapter 3 numerical methods. But the problem with numerical methods is that you have to discretize the object with element size of order lambda over 10. Then if the size of the object is several wavelengths or many wavelengths, the object is much larger than the wavelength, then you need many triangles to mesh the surface, often millions or hundreds of millions or thousands of millions of triangles. And your linear system will become very large. Now you have powerful workstations, you have fast solvers. Commercial software have often implemented fast solvers for the surface integral equations that are the ones that need less unknowns. And you can often solve in your personal workstation problems up to hundreds of millions of unknowns. No, sorry, not so much. A few millions of unknowns, yes, not hundreds of millions, a few millions of unknowns. But when I did my PhD, on high-frequency methods for a very simple reason. At that time, the amount of memory in computers was very small. It was about a few megabytes of memory. Also, numerical methods were at its beginning. There were a lot of work in method of moments and FDTD, etc. But at that time, there were no fast solvers. No fast solvers. The only way to solve the linear system was a direct or an iterative solution, maybe using a simple preconditioner, but there was no way to accelerate the iteration and to save memory. So the largest problem size that we were able to solve at that time was about objects of size a few wavelengths, maybe 2 wavelengths or so, not more than just a few wavelengths. In special cases like cubes, etc., we were able to solve larger objects, but for general arbitrary geometries model with a triangle mesh, just a few wavelengths. And at that time there was a lot of work in radar cross-section because there was a lot of interest in stealth aircraft, etc. So we needed to analyze large radar targets that were completely unaffordable by numerical methods. So there was a lot of work at that time in high-frequency methods, and my own thesis was a contribution to high-frequency methods, because it was the only way to analyze realistic radar targets at that time. Now, with fast solvers, with powerful workstations, you can analyze radar targets of up to 10, 15, maybe 20 wavelengths. Depends a lot on the methods you use and your hardware, etc. And if you use a supercomputer, you can analyze objects of hundreds and thousands of millions of unknowns. But high-frequency techniques are still interesting because they are widely used to analyze many kinds of antennas, like reflector antennas, for example, and they are still used to obtain fast solutions to realistic radar targets, because you don't want to spend, for example, I developed a software for high-frequency analysis of radar targets for monostatic RCS, a commercial software. I have sold a lot of licenses of that software, but And aircraft companies still use this software because it's very fast. High frequency methods are very fast because they don't need to solve a large linear system. They only need to integrate on the object surface and edges. But you don't need to solve a large linear system. So the solution is fast. What they do? Their high frequency methods are approximations. They do a lot of analysis of the target and design they design the target based on the analysis of high frequency methods because it is fast. And when they have reached a final design and they want to test more accurately, then they run a commercial software with multi-level fast multipole algorithm fast solver to validate the results of high frequency methods and check if the solution, the high frequency analysis that they use for the design is valid or not. If it is valid, it's okay. If it's not, maybe they have to do some small modification in the design. But anyway, they use my software or other because you obtain the solution in seconds or minutes to do the everyday trial and error design of the shape of the aircraft. And when they finish and they have a final shape to test more accurately, then they run multi-level fast multipole algorithm with a commercial software. It takes 1 or 2 days, and then they have a more accurate solution for the final specification of the radar cross-section. As shown in the picture, the high-frequency methods are widely used to analyze reflector antennas. The main approximation, the main assumption in high-frequency methods is the assumption of local scattering. That is, every point in the object surface scatters field independently of each other, as it was isolated in space. That is, the different points of the object surface or edges of the geometry of the object scatter the field independently of the other points, the same as if these points were not exactly isolated in space, because it depends on the local shape. But what I mean is that the different points of the surface scatter the field depending only on the incident field and depending also on the local geometry. And you can see this effect here. Here we have a surface reflection at that point. That is, we have an incident field coming from the reflector feeder. The incident field hits the surface at this point. Then the field reflects according to Snell law, to the well-known Snell law of reflection angle equal to incident angle. Okay. So according to this Snell law, we have surface reflection, and all points reflect the field in the same way. So if we have another reflection point here, it reflects the field in the same way. The reflection at one point depends only on the incident field and on the local geometry of the surface at that point. And there are many different scattering phenomena. For example, for these points that belong to the surface, we have surface reflection, but for other points like this here, we have that are on an edge, we have edge diffraction, and there are also other effects that we will see later. But the main idea is that we can analyze separately the scattering phenomena at different scattering points, because these scatter the field independently from each other. So since there is no interaction, there is no linear system to solve. You know that in numerical methods, the discretization of electric or magnetic field integral equations leads to a linear system, because you set the boundary condition for the total field at at different points in the scattered surface, and the field at a given point in the scattered surface depends on the field radiated by equivalent currents at all points of the object surface. So the field at one point is related to the field at all the other points, and this is what happens from the discretization of the electric and magnetic field integral equations leading to a linear system. This linear system collects all the interactions between all the source points with all the field observation points all together. But here, in high frequency methods, we don't have any linear system. The scattering is independent from one point to the other, so we only have to account the incident field at a given point, the local geometry, compute the scattering at each point, and this and all the other points in the object surface, and sum up all these contributions, and this summation of all the contributions is in fact a surface integral on the whole object surface, and also a line integral on the object edges to account for edge diffraction. The validity of this local scattering assumption is that the dimensions and the curvature radii of the object surface must be much larger than the wavelength. In practice, you know that it is not necessary that it is really much larger than the wavelength. It is enough if it is only a few wavelengths. Maybe just one wavelength could work in some cases, but it must be, in any case, the dimension of the object must be approximately larger than the wavelength. However, I said that the diffraction or the scattering at a given point depends only on the incident field. For example, scattering at this point depends on the incident field. Okay? On the incident field. However, sometimes there is a strong interaction due to a double reflection, like in this case, for example, for the dihedral. So in this case, clearly, the second point have incident field coming from the feeder, but also incident field coming from the other point. And the same happens for the first point, because of course we have also a reflection in this way. Okay, so here we have to account for multiple reflections, but we account for multiple reflections as an additional incident field on the surface. So for example, the incident field at that point is the field due to the feeder. Here the incident field at that point is the field due to the feeder plus the field reflected at this point that goes to the upper point. And in the bottom point, we have the incident field due to the feeder and the incident field due to the reflection at the upper point. So what we do is we trace rise. This is a ray tracing procedure. We trace rise following the different multiple reflections, and we account for all these rays as incident field on the remaining points of the target. So it can be a complex and time-consuming process to trace all rays and all multiple reflections, but there are optimized ways to implement this, and in practice it can be very fast. In my own software it takes just seconds or less than 1 second to do the ray tracing for a whole radar target, so it's anyway very fast. And it doesn't break the assumption of local scattering if you consider these multiple interactions just as a new or additional incident field on the point, on every point of the target. There are many kinds of many kinds of scattering phenomena. For example, the most important one is specular reflection. Specular reflection means that the surface behaves as a mirror, so we have an incident field and we have a reflected field pattern scatter field pattern at this point, where there is a narrow beam that follows a Snell law, so the direction of this beam with respect to the unit normal, the angle of reflection, is equal to the angle of incidence, with the unit normal at the surface at this scattering point. Of course, the unit normal will change from one point to another if the object has curvature, and we have to do this analysis at every point. So we have a reflected ray following a Snell law at all points in the surface. But we also have diffraction. This is the second most important scattering phenomenon. We have scattering diffraction or scattering at edges here, but also at tips, like here, or tips at the cone tip here. All these are diffraction phenomena, and what is interesting or important in these diffraction effects at edges and tips is that the scatter field travels in many directions. There is no longer a single or main reflection direction given by the maximum of a very narrow scatter field beam, but there is a spread of the scatter field in many directions, and this is important. We will address this topic later and at the last part of this section dedicated to high frequency methods. There is another important effect that you already know, is the presence of creeping waves. The incident field produces currents in the illuminated region, so initially the current at the shadow region should be zero, but however, when the polarization is in the plane of the tangent ray and the unit normal to the surface, we have a surface current wave. There is a current wave that travels along the surface following here the tangent ray direction, and this becomes a creeping wave in the shadow region. So we have a creeping wave traveling that way, coming back, going back to the radar, but also a scattering field in the shadow boundary. This is the reason why in the cylinder case with TE polarization doesn't have a shadow boundary. We already addressed this topic or this issue before, but the important thing is that creeping waves are also a significant scattering phenomenon that we can take into account. There are other phenomena of lesser importance, like for example the diffraction at surface discontinuities, diffraction at changes in materials. If we have a surface wave here, we have a surface current wave, and when it reaches the end of the body, we also have a scattering at the end of the body due to the abrupt termination of the surface current wave. We also have here, if we have gaps in the surface, slots, groove, all these are a kind of surface discontinuity that produce also scattering. Change in material, we have already mentioned that. We also can have scattering if we have a discontinuity at the surface curvature, not a discontinuity at the surface, but just at the surface curvature can produce scattering. So in fact, any kind of non-smoothness or discontinuity in the surface will produce scattering. If we have a real radar target like this aircraft here in the picture, we can observe that the different geometric parts of the surface produce different scattering phenomena. For example, here are the planar surface of the vertical stabilizer. We have a reflection. This reflection produces a very narrow beam, a very directive pattern, so it's a glint that we can see for this the reflection, and it is one of the most important contributions, not one of the most, but the most important contribution to monostatic radar cross-section, when the incident direction is perpendicular to the planar surface, the reflected field goes back to the radar, to the monostatic radar, and we can observe a flash, a flash glint at this surface. If at planar surface we have also reflections like this, multiple reflections. This is a case of double reflection at a dihedral. It is important because this also go back to the radar. Double reflections at 90-degree dihedrals go back to the radar for any direction of incidence. So also if the incidence is like this, the reflection goes back to the radar. It's important to account for this. We have edge diffraction, for example, at the leading edge of the wings or the trailing edge of the wings. We have also scattering at the slot between the horizontal stabilizers and the wing. We have if the radar radome is opaque at the frequency of the radar, then we have here surface reflection at the radar radome, but also creeping waves that go back to the radar and radiate in the opposite, in the shadow region. If it is transparent, we can have a cavity here, a cavity with the aircraft radar inside. And the engines and the inlet of the engines, we have cavities also. We have surface waves traveling along long parts of the surface. So you can see that there are a lot of scattering phenomena, and we can sum different contributions from different scattering phenomena, different parts of the object. But of course, we must know which contributions are more important, because it is a lot of work to derive the formulas to compute the field from different scattering phenomena. We have to write the formulation to compute the field. We have to implement this in a computer. It can be complex, so we have to account for the minimum amount of contributions that significantly contribute to the overall scattering. So we must know which are the most important contributions in order to sum only the most important ones and not all of them, because it would be a nightmare. It would be a very difficult task. So in order of importance, the most important contribution is reflection at planar surfaces. To give you an idea of the magnitude of the radar cross-section and the variation with frequency, here I define uppercase L as the strike, as the dimension of the object in the strike, if there is a strike line in the direction where we have a strike object, and A is the radius of curvature in the dimensions or the plane where the object is curved. For example, a planar surface like a plate, imagine for example here a square plate of size L. A square plate of size L has two strike dimensions, horizontal and vertical. So it has L dimension vertical, L dimension horizontal, and the reflection, the radar cross-section due to this reflection is proportional to L to fourth power over lambda over 2. So it's proportional to the square of the radar frequency. Now, the second most important is a cylindrical surface. So for a cylindrical surface, we have strike dimension L, and we have radius A. So the radar cross-section is proportional to L squared, that is the dimension in the strike direction L squared, times A, the radius of curvature, over lambda. So it's proportional to the frequency, not the square of the frequency, but now the frequency. a sphere, a spherical surface, or a surface with double curvature? Well, it's proportional to the product of the two radius of curvature. If it is a sphere, the two radius of curvature are equal to a, so a squared. No variation with lambda. We already know from the exact analytical solution of the sphere as a canonical object that the exact solution is a summation of cylindrical harmonics, etc. But this converges to pi a squared for radius much larger than the wavelength. So pi I squared is independent of frequency. Very important to know that for a surface with double curvature, like for example a surface with double curvature, the reflection, the contribution of the reflection at different points is independent on frequency. Now a straight edge. Here it is the object is like this. We have a straight edge of size L. This is L, okay? And the contribution is proportional to L squared, still independent on frequency. A curved edge of radius A has dependent on of the RCS as A lambda, so it's proportional to the radius and to the wavelength, so it decreases for in the large frequency region. And for all the other effects, from effects of order of contribution 5 and more, you can see that the RCS is proportional to a power of lambda, so it will be very small at high frequency, because at high frequency we have a small lambda. So in high frequency, the important effects are the ones that have power of lambda at a high power of lambda at the denominator. So the most important one in high frequency is reflection at planar surfaces, proportional to frequency to the square of the frequency, cylindrical surfaces proportional to the frequency, or spherical surfaces or straight edge diffraction that are independent on frequency. And these four effects, 1, 2, 3, and 4, are the effects that are commonly accounted for in commercial software for high frequency analysis. This and also creeping waves. These four together with creeping waves. My own software only accounts for these four and not for creeping waves. These four, 1, 2, 3, and 4, together with ray tracing for multiple interactions, ray tracing for multiple reflection surface as here, but not for creeping waves or multiple diffraction reflection. Multiple diffraction reflection is, for example, here we have reflection at a surface, then it goes to the leading edge of the vertical stabilizer and produces edge diffraction here. So we have diffraction and, reflection, multiple reflection and diffraction. So this is a secondary effect that is taken into account by some commercial software, but not by my own. Okay? So in practice, as I want to stress that we can obtain very reasonable results accounting only for surface reflection, planar and cylindrical or spherical surface reflection, and diffraction are straight edges or curved edges also. I integrate along the edges, so I implicitly also account for curved edges, so the effects 1 to 5 in practice, and ray tracing, and this is often enough. Well, here I finish this class on the general idea of high frequency methods and the main scattering phenomena in high frequency, and the next class will be dedicated to physical optics. That is the main scattering phenomena, because with physical optics you can compute the reflection at any surface, so effect 1, 2, and 3, reflection at planar, cylindrical, and spherical surfaces is accurately accounted for with physical optics. So in the next class we will be completely dedicated to physical optics, and with this we will account for the three most important effects. And in the last class, we will account for edge diffraction, that will be effects 4 and 5.